This is lab number 3 for Physics 2, Circuits. The purpose of this lab was to observe and predict the behavior and properties of circuits containing resistors and capacitors in various configurations. From these observations, we could determine generalizable rules about how capacitors and resistors function within a circuit and how they alter the current. There are 3 relevant physics concepts involved in this lab. The first is Kirchhoff's current law, which states that the sum of the current entering a junction is equal to the sum of the current exiting a junction, and Kirchhoff's voltage law, which states that the sum of the potential differences around a circuit loop is equal to 0. Additionally, we also used Ohm's law, which states that the potential difference across a circuit component is equal to its current times its resistance. Our first circuit is the one shown above. The measured current from both ammeters was very similar at 13.75 milliamps. This demonstrates that all points along a circuit in series have the same current, which is consistent with Kirchhoff's current law. When we flipped one of the ammeters, the current was the same magnitude but negative, meaning the same amount of current was going through the ammeter but in the opposite direction. Next, one of the ammeters was converted to a voltmeter through a setting on the device. Current reading on the other ammeter dropped significantly, likely because the voltmeter had a very high internal resistance. The voltmeter was then removed as a component in series with the rest of the circuit and used to measure the potential difference across each component, which is shown below here in the data. The sum of the potential differences going around an entire loop within the circuit should theoretically be 0, according to Kirchhoff's voltage rule. However, we found R's to be about 0.2 ohms. We figured that this is either because there's some resistance in the wires between components that we didn't measure, or it was due to fluctuations in the voltmeter's reading that created a margin of error in the measurements. When we attach the voltmeter, we alter the circuit. Why doesn't the ammeter reading change? The voltmeter has a large internal resistance, and because of this, when it is attached as a parallel component to the circuit, it draws a negligible amount of current, but just enough to generate an accurate estimate of the potential difference. The ammeter reading when the voltmeter was placed across the 100 ohm resistor was 14.9 milliamps, and the ammeter reading when a different resistor or a different ammeter was placed in parallel across the 100 ohm resistor was 37.6 milliamps. This occurred because the ammeter has a very small internal resistance, so when it's placed in parallel with the 100 ohm resistor, it decreases the total resistance of the entire circuit by allowing current to flow through it and bypass the 100 ohm resistor. And our calculations for the resistance on each circuit component are shown here on the right. This is our circuit to charge the capacitor. Upon connecting the circuit, it behaved as normal. However, over time, the brightness of the light bulb gradually decreased until it did not produce any more visible light. This is our circuit for discharging the capacitor. Upon connecting the circuit, the light bulb lit up immediately. However, over time, the brightness of the light bulb gradually decreased until it did not produce any more visible light. Both the charging and discharging circuits behave the same whether we use a 10 or 20 ohm light bulb. This behavior occurred because in the charging circuit, current flow initially starts at the maximum, then decreases when the capacitor gains charge. Conversely, in the discharging circuit, current flow initially starts at the maximum, then decreases while the capacitor loses charge. We got a similar chime between the charging circuit and the discharging circuit for the light bulb to fade to 0, and that's likely due to the capacitor either gaining or losing the same amount of charge. What if you charge a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If there is no resistor in the circuit, the ideal model would predict the capacitor to reach full charge instantaneously. As R approaches 0, dq over dt approaches negative infinity according to the equation seen below. However, this would not happen in real life. Wires still have internal resistance, so dq dt would have a very large but finite value. The capacitor, therefore, would be charged very quickly, but not instantaneously. Also, electrons flowing through the current cannot move faster than the speed of light. In conclusion, Ohm's law and Kirchhoff's laws are useful in determining the properties of components of a circuit. Resistors can generally be used to reduce current by placing them in series or increase current by placing them in parallel. And capacitors can be used to store and release charge based on specific configuration of the circuit they're in.